Okay, students, welcome to video class 29. And in this video, also, we're continuing the study on Bode plot, stability analysis using Bode plot, part 2. Okay, so in the last class, I have just introduced this Bode plot, which is absolutely a new topic as far as you are concerned in all the standards. Now, anyway, the base of all this is the frequency response we have seen. Now, we have also seen that Bode plot actually consists of two plots, that is the magnitude and the phase. Now, magnitude and phase of what? Of an open loop transfer function, and it is not simply an open loop transfer function. This is a sinusoidal open loop transfer function. Now, what do you mean by sinusoidal open? Now, an open loop transfer function is given by g of s, h of s. Now, when you substitute s to be equal to j omega, then that is actually your sinusoidal open loop transfer function. So I'll just show you the previous slide which we have seen. So we have got a generalized expression. I'm not going to write it again and again. So we know that this g of j omega is k into 1 plus j omega t1 into 1 plus j omega t2 divided by j omega raised to n plus j omega ta into tp. Now, what you need is, we need now from this given transfer function, we will be finding out the magnitude and phase. Now, the magnitude is usually expressed in decibel, while the phase is shown as such. And once if you represent that in decibel, we will plot that with respect to the logarithmic scale of omega. Phase is also plotted along with the logarithmic scale of omega, and I have explained why we are using logarithmic omega in order to accommodate the low frequencies as well as large frequencies in a single graph sheet, so that it will be easy to understand how it varies. And now this consists of magnitude and phase plot. Now, coming back to this circuit, so we have expressed this in terms of decibel as 20 logarithm of the magnitude of this. Now, magnitude in decibel is found out like this. So you can see that this is 20 logarithm of magnitude of this, or you can see that this can be expressed as the sum of the magnitude of the individual terms. So if you have an idea about how each term varies according to the frequency, then what you need to do it as per the logarithmic, or as if it is expressed in decibel, you just need to add them up, add the effects of each terms, and you will be getting this magnitude plot. And while drawing this, we are not interested in the arbitrary values of omega. Now, what I mean by arbitrary value is simply, now when you plot a graph, something like a f of t is equal to t square, say for example, what's the meaning of arbitrary value? I will be putting some values of t, say 0, 0.1, 0.6, 3, 2, 2.5, and so on, and you will be finding out different values for this f of t. This is the meaning of arbitrary, putting the values, and you will be say plotting each point, and you may be plotting, and you may be getting a graph like this, right? So this is how, so you are getting an almost an accurate plot of this f of t. Now, in this case, we are not interested in that accurate plot. We are interested in the variation of this of the magnitude as omega varies. Now, the thing is that omega, we know that omega is expressed in logarithmic scale. So I'll just give you the concept of decade. There is something called as a decade. So, for example, I'm going to vary this omega and find out this logarithm omega. Say, for example, I'm starting with the 1 radians per second. Do remember what we are using, the omega always is expressed here as in radians per second. Now, if it is 1 radians per second, we know that when you take the logarithm of 1, that is equal to 0. So this is 0. That is the logarithmic scale of, don't say that this is not decibel. This we are doing only in the case of frequency. Magnitude is the thing which is expressed in decibel. So do remember that. So this is 1 radians per second. The logarithm of 1 radians per second is 0. We know that. Then you have 10 radians per second. Now, when you have 10 radians per second, the logarithm of 10 is 1. If you have 100 radians per second, then the logarithm is 2. So remember, look at this. Now, this omega is having a great variation from 1 to 100. Now, when omega varies to 1 to 100, log actually varies from 0 to 2. So that's why I told you to accommodate the lower and higher frequencies in a single graph. So now coming to this, look at this variation from 0 to 10. Now 10 to 100. Now the next is we'll see one more thing. 1000 radians per second, it will be 3. So what is the change across each? What is the similarity of the change? Now when you look at this, you can see that each change, each level is actually a multiple of the previous. The multiple of 10, right? Now when 1 is multiplied by 10, you will get 10. When you 10, you will get 100. So that means you can see that as omega varies from 1 to 10, you can say that omega varies in a decade. So where the omega is said to vary in decade. So this is 1 decade. What's the next decade? As omega varies from 10 to 100, we call that has passed another decade, right? Now when it changes from 100 to 1000, so in the logarithmic scale we say that this variation actually represents 1 decade, this variation the next decade, and this way next decade. So each decade is actually the multiple of 10. So you need to understand that. That is how frequency gets varied, and we are interested in the magnitude of this in decibel as the omega varies in decades. We are not interested in all the values in between. We are interested in how this magnitude varies as omega varies in decades. Okay, so hope you understood the variation of that. So now, since we have represented this in magnitude and that too in decibel, now once if you find out the effects of each terms, you can just take a sum of that. You don't need a multiplication, and obviously that's going to be much easier. And not only that, since we are not plotting it by arbitrary values, that's not going to be exactly accurate, but even though it is not accurate, I mean the error will be less than 3 dB. Okay, so as you know, in a practical case, we always tolerate up to 3 decibel. Okay, so there's not going to be any error difference. The error difference will be negligible, so it is enough to find out the variation by using this. You don't require the exact value of the magnitude. Now coming to the phase of this, we know how to find out the phase. Now the phase is plotted by each term will be, okay, so here in this you are adding up each magnitude individually. Similarly, the phase is also, you're adding up the phase individually, just as it's very simple, straightforward representation. Now this graph, now when you plot the phase, we just simply plot exactly as we have plotted here, just putting some arbitrary values of omega, and you will be plotting an exact graph. Okay, but the magnitude we are interested, we will be representing in asymptotes or straight lines. Therefore, this Bode plot is also called as an approximated asymptotic plot, and that is enough for the analysis. Now, coming to the when you have a closer look at this transfer function, we can see 4 different terms. In the previous video, I have also introduced you a 5th term, which we will be dealing in the separate session. So for the meantime, let's not club with that. We just we are going to identify 4 terms. Okay, from now, that is, one is a constant term k, another one is of the term 1 plus j omega t1, another term is 1 by j omega ta, the last one is 1 by j omega raised to n. So I'm going to rewrite it again for you. The 4 different terms that we have identified, that is the constant term k, second term is 1 plus j omega t, right? Okay, there it is, t1. I'm just using t. Now third one is of the form 1 plus j omega 1 by 1 plus j omega t, and the fourth one is 1 by j omega raised to n. Okay, so these are the four terms which we have identified, and we can see that, look at this. Now coming to this expression, this here you cannot find any omega, so this term is totally independent of omega, meaning if you are going to find out the magnitude and the phase of this term, you can see you will be getting a value which is totally independent of omega, meaning that is going to be constant throughout all the frequencies. Okay, so there is no variation for this, that will be a constant. Now, while in these three cases, here you have an omega, well, in these three cases, you can see that the magnitude as well as the phase depends on these three terms, depends on what is called as frequency, depends on frequency. Okay, now what we are going to do is, before going to have a Bode plot, we need to understand how this varies according to frequency, what is the magnitude and phase. Now we will, in the next session, we will be studying separately the magnitude and phase of each terms. So number one, magnitude and phase of the first term, which is constant k. Okay, constant k. Now what is the magnitude? Let us start with the magnitude. The magnitude is usually represented by in decibel. So this is 20 log k, right? Now, for example, if I am putting k to be equal to 10, then the answer, the magnitude is 20 log 10, which is equal to 20 decibel. So this is 20 decibel. Now, if k is equal to 100, then this will be 20 log 100, which is 100 is 220. This is 40 decibel. Now look at this. You have got a constant answer, 20 and 40 dB. When you try to plot this magnitude with respect to frequency, you will be getting a straight line, because this is throughout 20 dB over the whole range of frequencies starting from 0 to infinity radians per second. That's the meaning of this. So this term will be having what is the effect of this term in the transfer function? So the transfer function, the magnitude, this will be offering, this k will be offering a constant magnitude for this transfer function, which is totally independent of frequency. Throughout the frequency, you will be having this what is called as the magnitude. Now coming to the phase of this. Now what do you mean by phase? How will you find out the phase? Now if suppose you are having the term like a plus jb, then the phase is defined as tan inverse b by a, that you know, right? Now what is the phase of a constant term? Now k can be written as k plus j0, right? So what is the phase of that? Phase is tan inverse 0 by k, which is equal to 0, right? So that means when you have a phase plot of this particular term, you can see that as omega varies, this will be always having a phase of 0. So no phase change results in the case of what? In the case of this constant term. So constant term is not going to have any impact on the phase change, whatever may be the constant, be it 10 or be it 100. The only thing that changes is the magnitude. That is not going to, whatever may be the value of omega, that's not going to be affecting the phase. So the phase of the signal which passes through such a control system having a transfer function will not be affected by the value of k, but the magnitude does. Okay, so this is a picture of the magnitude plot of this term and the phase plot of this term. Similarly, we are going to study magnitude and phase of each terms. That's the next. Okay, now you have a term 1 plus j omega t. This is again of the form a plus jb, right? Now what is the magnitude of this? We know that the magnitude is root of a square plus b square. Now using that, now you want this magnitude in decibel, right? So if you want the magnitude in decibel, you need to multiply this magnitude by 20 log. So you need to take the logarithm of that. 20 logarithm of 1 plus omega t the whole square. This is actually the magnitude of 1 plus j omega t. Okay, so this is just like this. So if you don't understand, you may just look at this. 1 plus j omega t, 20 log magnitude of 1 plus j omega t, which is 1 square plus omega t the whole square. Now, as I already mentioned to you that we are not interested in the exact value of the variation. We are interested in the variation of this gain as frequency varies in decades, varies as a multiples of 10. Okay. Now, let us see how to plot this or how to find out that change per decade. Okay, so that change we will be denoting as per decade. So you are going to get the unit is going to be this much decibel per decade. This is actually, so this denotes what? This denotes the change in the magnitude as the frequency varies in decades. Okay, so we are interested in that. Let's see how to plot this. Now, see, so there can be, so you can see two terms, 1 and omega t. So depending on the value of this t, this omega t can be much less than 1. So there can be two cases where one is omega t is much less than 1, or you can have a situation where omega t is much higher than 1. Coming to this case 1. Okay, this case. Now when omega t is much less than 1, what's going to be your magnitude? If it is much less than 1, you can ignore. So I told you this is an approximated graph. So you can simply ignore for a very low or insignificant values. Say for example, if omega t is 0.01, right? Now what's going to be 0.01 square? That will be again less than 0.01. That means it comparing to 1, that's going to be so feeble. So you can neglect. So in this case, you can neglect what? Neglecting omega t. So this becomes 20 logarithm of 1, right? Root of 1, which is 0 dB. Okay, now coming to this side. Now in this situation, in this scenario where omega t is much greater than 1, say for example, if your omega t is say some 4 or 5 now or 6, your omega t square is going to be 36, right? Now comparing to 1, that's going to be 1 you can actually neglect. So what will be your magnitude in decibel, which will be root of omega t square or log omega t. Okay, so this is 20 log omega t dp. Okay, so this is actually your magnitude in this scenario. So we have seen two conditions where omega t can be much less than 1. There, as long as it is much less than 1, the magnitude is 0 dB. That means the magnitude this particular term offers to the transfer function is 0 dB. That's what it meant. Or in other words, you can say that for some range of lower frequencies, it is as if you don't have a term like 1 plus j omega t, even though you have that, because that's not giving you any change in the magnitude. The magnitude remains as 0 dB. So from that you can come to a conclusion that this particular term is not going to have a term as long as it is omega t is much less than 1. Now this will be active only as omega t becomes greater than equal to 1. Greater than 1. So that means this is equal to 20 log omega t decibel. Now I'm going to explain the meaning of this magnitude. How is so? That means you can say we do not know this omega t, or you can say from this you can come to another conclusion that omega is much less than 1 by t. So let it be 1 by t. Okay, let this point be so till this point we can simply assume that this less than this term, which is omega is less than 1 by t, this is 0 dB. But what is the meaning of this after this? So we are going to plot the same graph after 1 by t. So after 1 by t, what happens is omega is much greater than this 1 by t. Now as it moves greater than 1 by t, how will we plot this? Okay, now let us see the variation of this. Okay, Now let us see the variation of this. Say I am going to put omega t, okay, and find out the magnitude in decibel. Say let the omega t be 1. What is 20 log 1? Which is 0 dB, right? Now I'm changing this to the next decade. The next decade is 10. So as the frequency changed to 10 radians per second, what is its magnitude? 20 log 10, which is actually equal to 20 decibel. Log 1, log 10 is 1, so this is 20 decibel. Now as it moves to the next decade, which is 100, you can see that this is 20 logarithm of 100, which is actually log of 100 is 2, so that 2 into 20, which is 40 decibel. Now I'm going to put one more value. Say for example, if omega t is 1000, this is going to be 60 decibel. So everything it is positive. So magnitude of this is plus 20 decibel. So what you can find out this is regarding a speciality of this 1 plus j omega t is, after a particular frequency, after it achieves this, as the frequency becomes much higher in comparison to 1, you can see a variation of this term as 20 decibel. So it increases. This is, since the positive sign shows that this increases. This particular term increases by 20 dB in every decade, right? So in this decade it changes to 20 dB. In this decade it changes to another 20 dB, resulting in 40 dB. So what you can say of this variation, you can simply say that this offers a 20 decibel per decade rise. So 1 plus j omega t, the magnitude of 1 plus j omega t, the magnitude of 1 plus j omega t rises by 20 decibel for every decade, right? For every decade, right? So now, so you have understood. So we have considered two scenario where omega t is much less than 1. We found out to be 0 dB, and for greater than 1 we can see that it increases at a rate of 20. So there must be a 1 by t, which is a frequency. Now assume that you have another decade. The decade point is somewhere here. That is the multiple. See the 10 omega. Say for example, this is your 10 omega and this is your 100th omega. Then say this is the meaning of this. So when it reaches this value will be 20 decibel per decade, right? If this is a decade, if this starts from here, so far to this point, this is 0 dB. Now once this reaches over here, what is the magnitude? The magnitude is 20 dB. That's the meaning of this. This keep on rises and reaches 20 dB at the next decade. That is, say for example, if I am considering this as 10 and this one as 100, I can see that this particular graph varies accordingly. Okay, now we have seen that for some lower frequencies this is having 0 dB. That is, for lower frequencies it is as if this term is not existing in the transfer function, right? This is not offering any magnitude to this particular transfer function. So that is and after a particular frequency, what happens is it starts to increase at a rate, and you will denote that rate as 20 dB per decade. Okay, this is 20 dB per decade. Okay, now what's the next point? Now the next point is, if you want to draw this is an important aspect. So how will you find out this? Okay, now how will you find out this? Now the way in which it can be found out is, now clubbing these two scenarios together, we can see that this particular 1 plus j omega t varies. For a lower frequencies it is 0 dB, for a higher frequencies it is 20 dB per decade, and it goes on like that. Okay, right. So this is how it moves. Now we are interested in this frequency. We should know, then only we will be able to draw the graph. So at from which frequency onwards this starts to give a rise. That's what we want to find out. That is, or it is the frequency at which both the condition is met together, right? So in other words, if you can equate the magnitude during this condition to the magnitude during this condition, you will be able to find out this omega. And that is nothing but this is 20 log omega t. That is the magnitude during this time, this scenario. And this is equal to 0. That is the magnitude during this scenario. So what is this omega t? Omega t has to be equal to 1, or omega is equal to 1 by t. Okay, so this frequency is actually 1 by t, and this is called as the corner frequency of this term. The corner frequency of 1 plus j omega t. Okay, this is very, very, very important. So what is this? This is actually 1 by t. For example, I'm going to consider, say, 1 plus j omega 0.2, right? Now this is, so what is this? What's the meaning of this 1 by t? 1 by t is actually the reciprocal of the term that comes along with what? Along with the omega. Okay, or in other words, along with the j omega, right? So along with j omega, so this is, look at this. So this is actually 1 by t is the reciprocal of the term that comes along with the j omega. So what is the term along with j omega? Here it is 0.2, or the omega is equal to 1 by 0.2, or this is equal to 5 radians per second. Now in this, for this term, the corner frequency is actually 5 radians. Omega corner is actually 5 radians per second, and later you will understand the sense. So this is very important, because this is the point from where we need to draw this as from 20 decibel per decade. Okay, right? Okay, now this is 20 decibel per decade. Now next one is 1 plus j omega, say I'm going to use, say, 2. Okay, 1 plus j omega 2, and again you can see that the corner frequency is, what is the corner frequency? Corner frequency is 1 by 2, or it is equal to 0.5 radians per second. Okay, so if you are to plot this graph, you will see that this particular term starts at a 20 dB per decade after 5 radians per second, while this term starts in this way, right? So this will be starting from 0.5 radians per second in 20 dB per decade. So both the cases, the frequency, the magnitude rises at a rate of 20 decibel per decade, but at two different frequencies. So these frequencies are called as a corner frequency. So it is the corner frequency actually distinguishes each numerator terms. This can be called as the 1 plus j omega t terms in the numerator, right? So each one will be having its own corner frequency. Now another, what is the relevance of this corner frequency? So you can come to a point that till the corner frequency, okay, 1 plus j omega t, the magnitude of 1 plus j omega t is 0 dB, or in other words, in the case of a magnitude plot, this particular term will not be having any effect till the corner frequency. Okay, so that's the reason why this corner frequency of this term is so important in order to draw the Bode plot. Okay, so this is all about the magnitude of this term, and you will understand as we do problems. Okay, now let's see the phase of let's see what is the phase of this 1 plus j omega t term. Now what is meant by phase? Phase is actually tan inverse b by a. This is tan inverse omega t. So see, you don't need any decades variation, or you're not interested in that. You're simply interested in the in the arbitrary values of omega. Say substitute some values for omega, find out the phase, just as we do a normal graph. Put some arbitrary values and find out the phase, and you can have the plot phi versus again logarithmic omega. Okay, so that's the speciality. Now you will be getting a graph and you can have a freehand drawing of that. Okay, now what we do is, in a Bode plot we actually combine this magnitude. Once you get we need a combination of this magnitude plot and phase plot. Okay, now on one side you have a vertical axis in a semi-log graph paper. You can see that the vertical axis is actually the normal graph. So there you can you can have the normal variation. So you can plot magnitude as well as phase on those two sides. Okay, now this side, the zero line, or this can be noted as 0 dB, while you must see that this 0 dB has to be in line with, in this side you can plot the phase. So you can just draw the, so that must be marked as minus 180 degree. Okay, so this is a very important thing, because this 0 dB line in magnitude is a thing which is actually determining something, and we have already understood when we found out the corner frequency. 20 log omega t 0 means it is equated to 0 dB, or it is the frequency at which it starts. So everywhere the main when you plot the magnitude plot, the effective magnitude plot, the frequency at which that gain touches this 0 dB is an important point. We'll come to that anyway later. You don't have to, I'm not going to confuse it anyway. So similarly, in the phase plot also, minus 180 degree is just as a 0 dB line. So minus 180 degree has to be drawn in line with this minus 180, and you can simply, so from this this is the axis where you plot log omega. Okay, so this is 1, then you have 10, 100 and so on, right? So you can have the plot. Okay, so you will be having a magnitude plot as well as the phase plot in the same graph. Now on comparing these two plots, we can find out, or we can say many things about the stability of the system, or this gives you a more wider picture of the relative stability. Okay, now the next is the magnitude and phase plot of 1 by 1 plus j omega t. So let us see the magnitude in decibel. Now when you represent this magnitude in decibel, this is 20 logarithm of the magnitude of 1 by 1 plus j omega t, right? And this is quite similar to the previous one, so I'm not going to spend too much time on that. This will be 20 log, okay, and this magnitude will be root of 1 plus omega t the whole square, right? This is the magnitude, and this can be written as minus 20 log of root of 1 plus omega t the whole square. Okay, so there also, as we have studied, you can have a scenario where omega t is much less than 1 and omega t is much greater than 1. So in this case, during this case, the magnitude will be 0 dB, while in this case, this will be, the magnitude in decibel will be equal to minus 20 log omega t. Now what is the meaning of this? Okay, now let us see. omega t and magnitude. Now, as you can see that at omega t is 1, the magnitude is 0. When omega t is 10, this will be log 10 is 1. So this will be minus 20. When it is 100, this becomes minus 40. So as the omega varies in decades, you can see there is a change of minus 20 dB. So when you plot this, you can see that, say, when you plot this, you can see that for a range of frequencies, this will be 0 dB, and after that, after a particular, so that is till that point it becomes 0 dB. After this point, instead of going in this way, this particular term goes in this way. This is actually minus 20 dB. If this is positive dB decibel, this must be minus dB. So you will be having exactly the same slope over here, but in the negative direction. That's all. So this is actually minus 20 dB per decade. Okay. So you can see that this 1 by 1 plus j omega t, 1 by 1 plus j omega t offers minus 20 dB per decade to the transfer function. Okay, minus 20 dB per decade to the transfer function, right? So how will you find out this point? This is again, so it is actually what is the nature of this point? It is this point where these two conditions meet together, or the magnitude remains the same. So this will be minus 20 log omega t is equal to 0, or omega, you can find out again, it is equal to 1 by t. So what is the speciality of this 1 by t? The speciality of this 1 by t is the frequency at which this factor starts to decrease at a rate of minus 20 per decade, and less than that frequency, this is having no effect. That is, as I told you earlier, as if you don't have such a term in the magnitude, right? And this frequency is again called as the corner frequency. This is called as a corner frequency of this term. Okay, right? Same. So say for example, just give you one example, j omega 0.1. What is the corner frequency of this? Say for example 1 by 1 plus j omega 0.1. It is simply the corner frequency is actually equal to 1 by 0.1, or this is equal to 10 radians per second. Now if you try to plot this, what you can see that still 10 dB, 10 radians per second, this will be 0 dB, and after 10 radians per second, this is going to fall. This is called as a fall of minus 20 dB per decade. Now what will be the phase of, phase is nothing but, it is say the term is 1 by 1 minus 1 plus j omega t, right? So the phase is, how will you find out the phase of the numerator by denominator? The net phase of this term is 0. The net phase of this term will be tan inverse omega t, right? So the effective will be the numerator minus the denominator. So this is going to be minus tan inverse omega t. So for example, if 1 plus j omega t is plotted, you may be getting a graph like this. Okay, you may be getting a graph, say something like this. And if that is the case, in this 1 by 1 plus j omega t, the phase is exactly in a reverse direction, right? So this is going to be like this. This is going to be like this. Okay, so this is minus 45 degree. So this is the point at which this is my 1 by t, and at 1 by t here also you are going to get 45. Why 45? Because this becomes omega t becomes 1, tan inverse 1. What is tan inverse 1? Tan inverse 1 is either 45 or minus 45. Okay, so in this term you will be getting a phase diagram like this. In the other term which we have studied, you will be getting a phase diagram something like this. Okay, so hope you understood how to find out the magnitude plot of this. Right. Now the next is actually we are going to study about the magnitude. So this one is the third point, I think. Okay, this is third. Right. Now the fourth one is the magnitude and the phase of 1 by j omega raised to n, which is another important thing. And this is usually, even though we have separated the constant term and this term separated, but when we draw the Bode plot, we will combine these two terms together. So that has got a relevance that you will understand later. Anyway, let us try to find out the magnitude and the phase of this term. Now, what is the magnitude of this term? That is 1 by j omega raised to n. So, now let us see how will you find out this magnitude. Now, this is actually the magnitude in decibel is going to be 20 log 1 by j omega raised to n. Okay, the magnitude raised to n, the magnitude of this. Now we know that the magnitude of j omega is omega itself, root of omega squared, which is omega itself, or omega raised to n, right? Or this can be written as minus 20 log omega raised to n, or this is equal to minus 20 n log omega, right? Now what is the meaning of this? This particular suggests that so when you look at the magnitude of this, what can you say about the change in the magnitude of this factor? So for that, say assume that n is equal to 1. What is the meaning of n? N is nothing but, see, you must know that term, that is j omega raised to n. I've already told you the importance of n. N refers to the type of the system. Now assume that you have a type 1 system. In the case of a type 1 system, type 1 system, the magnitude is going to be minus 20 log omega. Okay, this is very simple, minus 20 log omega. There is no t and no corner frequency. So that means this particular magnitude varies from 0 to omega. There is nothing called as a corner frequency for this. Okay, so this actually has got values for every. So as you start from 0 itself, you will be having. So let us just find out as you vary omega, what is this magnitude. So at 1, this will be 20, when omega is 1, this is minus it is 0, and when omega is 10, this will be minus 20. When omega is 100, this will be minus 40. So what you can say about the change? This particular term offers a minus 20 dB per decade from the 0 frequency onwards. That's it. Or from the lowest frequency onwards, it is offering a change of minus 20 dB per decade. Okay. Now what if n is equal to 2? If n is equal to 2, that means then this will be, the magnitude is going to be minus 40 dB per decade. So for a type 2 system, it offers a fall of minus 40 dB per decade. So when you try to draw this, you will be getting like this. Say it starts like this, right? So it starts like this. It will be always a fall of minus 20 dB per decade for n is equal to 1, right? For n is equal to 1, it will be like that, right? And then next is, okay, so this will be having always a slope of minus 20 dB per decade. So that's what we need to understand. There's nothing like corner frequencies or anything like that. Now what about the phase of this? When you find out the phase, it's nothing but that is 1 by j omega raised to n, or the phase is given by minus 90 n degree. Okay, so for a n is equal to 1, for a type 2 system, the phase is minus 90 degree. So here also you can see that this term is offering a constant phase of introduces a constant phase of minus 90 degree throughout the frequency. Okay, hope you understood this, right? So these are the variations of magnitude and phase of the four terms which we have identified. So you may go through this thoroughly, and in the next session we are going to start doing problems of Bode plot. So you must be ready with your semi-log graph paper. At that time I will be explaining how to draw this especially the magnitude plot. The other plot, it is very familiar to you, phase plot, but magnitude plot, it needs some discussion. Okay.